All right, for this lesson, what we're going to talk about is sort of the advantage that simple machines actually give us. Okay? Sometimes it can be a force advantage, sometimes it can be a distance or a speed advantage. In this case, if you look at the force in our example here, even though the load force is only 36 newtons, we only need 12 newtons to be able to lift that load force. And so we have an advantage. Right? In this case, specifically, 36 divided by 12 is 3, meaning we only need to provide 1/3 of the force required to lift it. Right? Or the load force is 3 times greater than what we actually need to apply. So we call this a mechanical advantage. And if we look at our static equilibrium here, or the law of the lever, and we rearrange it, we get that force ratio that we just calculated. But we also get this distance ratio. Now in a perfect world, these two ratios, the force ratio and the distance ratio, would be equal. But it's not a perfect world, and so they're not equal. And they're not equal because, well, the distance ratio will always be true. You can measure that with a ruler. But the force ratio isn't always perfect because in any simple machine or complex machine, there's always going to be frictional forces that will remove some of that energy. So not only are you trying to, say, use a simple machine to lift something, but you're also trying to overcome those slightly additional frictional forces that are present in your simple machine, and they'll always be present. So, all right, so because there's always going to be frictional forces present, this ratio won't always equal this ratio. Okay, because you're always going to be fighting some sort of frictional forces inside of your simple machine. So, we call that distance ratio the ideal one, because that is what would equal the force ratio in a world without friction. But in a world with friction, this is the actual mechanical advantage we get. So this is what we call the actual mechanical advantage. Okay, now in the real world, they won't be equal. Okay, in an ideal world, they will be. And since, if you look at the units, here we have meters per meter, which cancels. Here we have newtons per newton, which cancels. Okay? What happens is we get a dimensionless quantity, meaning ideal mechanical advantage and actual mechanical advantage have no units. All right, so let's actually look at mechanical advantage in a couple problems. So those are our equations. Here will be our first problem. Question 1. So here we have in an acrobatic demonstration, one person jumps onto the end of a plank. Here we have a lever. Right? This creates a large effort force right here of 920 newtons. That's our effort force. At the end of the board, at a distance of 1.7 meters, now this says from the fulcrum, so that is our distance arm, or sorry, our effort arm, which is 1.7 meters. You have a smaller person here, which is a load force of 460 newtons, so that's our load force, 460 newtons, and located 3.1 meters from the fulcrum. So we know that our load arm is 3.1 meters. Calculate the AMA of the board. So that's your actual mechanical advantage. So for our actual mechanical advantage, we are comparing the forces. So load force over effort force. Okay, our load is 460. And our effort force is 920. So our actual mechanical advantage is 0.5. And that's it, just 0.5. There's no units associated with that. If you wanted to calculate the ideal one, right, you would do dE over dL. It would be 1.7 divided by 3.1. And you notice it would be 0.55, but we don't need to do that. The question doesn't ask us to. Okay, but you'd notice that the actual, again, will always be slightly lower. I should write that up here for you. Okay, your actual mechanical advantage will always be slightly less than your ideal mechanical advantage, because this could definitely be a test question because of frictional forces that are always present in any kind of machine. Even if you took that machine and threw it into space, doesn't matter. Those machines still have interacting parts. There'll be those internal frictional forces will be present there, always. All right, so let's move on. We'll look at question 2. Question 2 does say to calculate the IMA. So we just did that, but all right, we'll do it again. So IMA, the ideal mechanical advantage, is our distance arm ratio, which in this case would be our effort arm was 1.7 and our load arm was 3.1. So we got 0.55, which, like I said before, is greater than your actual one. Right? Your ideal will always be the greatest one in a frictionless world. So we've talked about this ideal mechanical advantage always being greater than your actual mechanical advantage. Right? But you don't want that difference to be too big, because you still want your simple machine to have some kind of advantage to it. So in most simple machines, we try to reduce those frictional forces as much as possible. And this is something we call efficiency. So if we compare our actual mechanical advantage to our ideal mechanical advantage, the closer those numbers are to each other, the more efficient our simple machine is. Right? If you manage to get your machine to have as little friction as possible, then actual will be very close to ideal and you'll have a high efficiency. Okay? Which is what you want. Right? The more friction you have, the less your efficiency is. And we can calculate this as a percentage. So let's try question 3. Okay, so here we have a 14 Newton cart and is pulled by 1.2 meters, up a ramp with an effort force of 5 newtons parallel to the ramp. So here everything is nicely labeled for us in the question. Raising the cart 4 meters above its final level. All right, so in this case, our simple machine is an inclined plane. All right, so we're pushing something up an inclined plane, right, which is a total distance of 1.2 meters, but we're only raising it up to a height of 0.4 meters. Right? And it is taking us an effort of 5 newtons to push it up the ramp, where it would have taken us 14 newtons if we had lifted it straight up. So the ideal mechanical advantage is our ratio with our arm lengths, which is 1.2 meters over 0.4 meters, which is 3.0. Okay, so that's in an ideal world with no friction. But we know when we push something up here, there's going to be these frictional forces, right, that are trying to oppose the motion and therefore oppose us in trying to complete our task. So the actual mechanical advantage, we compare forces. Okay, our forces are 14 newtons, 5 newtons, which is actually only 2.8. So even though it should only take us 1/3 the amount of force to push it up. Right? It actually takes a little bit more than that because of those frictional forces. So how efficient is this ramp? Well, we can calculate the efficiency by comparing these ideal and actual mechanical advantages. So AMA over IMA. And once we do that, we can times it by 100% to make it a percentage. So we have 2.8 over 3.0 multiplied by 100, and we get 93%. Okay, so that's not too bad. That's a pretty good, efficient, simple machine. All right, for our last question, we have a pulley system being used to raise a shipping container from the dock to a cargo ship. Okay, so a pulley system raising something straight up. Here's our effort force. And it's required to lift a mass of this. Now, this is very, very tricky. This is the load, but that's not your load force. That's simply the mass. So if you want to know what your load force is, since we're lifting a certain mass, we are lifting its weight. And the weight is the force of gravity, which is mg. So we'd have to actually calculate what the load force is first before we move on to calculate the efficiency. So this is part A, calculating the load force, which would be your mass, 35,000 kilograms, multiplied by G, which if you remember is 9.8 newtons per kilogram, and we get a load force of 343,000 newtons. Okay, now that we have that, we can calculate the IMA, the AMA, and the efficiency. So let's start with the ideal, the IMA. Right? The ideal mechanical advantage compares our arm lengths. Right? And they tell us this right over here. So the effort force moves 54 meters. So that's our first one. While the load is only raised 8.7 meters. So that's our second one. So that gives us an IMA of 6.2. It's a pretty large advantage. But in reality, we need to find the actual mechanical advantage by comparing the forces. And so you have your load force, which we calculated in part A, 3.43. Move this over, running out of room, times 10 to the 5, divided by the effort force, which is here in the question, 6.8 times 10 to the 4, and we get 5. So not as high, but like I said, that'll always be lower because of those frictional forces. So to find the efficiency then, we can compare AMA and IMA and multiply by 100%. Right? So your AMA is 5, your IMA is 6.2. Multiply that by 100%, and we get an efficiency of 81%. All right, one more thing I want to mention is we've gone through a couple examples of simple machines, but a lot of machines are actual complex or compound machines, which are a combination of simple machines. So let's say, for example, I attach this pulley system to raise up some object, but I have it raise it up an incline. Right? Now, you would multiply your mechanical advantages right? Because you get even more force in your load for less effort. So your mechanical advantage would increase, but your efficiency wouldn't increase because now you have to deal with more frictional forces. So if you wanted to figure out your efficiency, right? I get some students adding efficiencies. Some students find the average of the two efficiencies. But what you want to do is you want to multiply the two. Now this is very important. When you multiply percentages, you do not multiply 93 with 81. A percentage is really a decimal between 0 and 1. Okay, so what I would do is I would say our total efficiency equals the first one, which was 93, but that's 0.93, multiplied by the second one, which is 81, which is 0.81, which gives us a total efficiency of the two machines together of 0.75, or 75%. Okay, so the more simple machines you add together, you just can't avoid it, the more frictional forces you have to deal with, and your efficiency drops. But again, the more simple machines you add together, your mechanical advantage also multiplies, and so you have a much, much higher advantage. That's the way machines are going to go.